Welcome to the architecture of modern artificial intelligence. I'm glad you're here. This is episode 1 of a comprehensive AI learning program spanning 8 modules and 24 sessions. We'll cover everything from the fundamentals of AI and machine learning to tokens and transformers, prompt engineering, agentic AI, hands-on coding tools like Cursor and GitHub Copilot, AI content generation, and finally, production enterprise deployment. Whether you're a business leader, a developer, or simply curious, this series is designed to give you a real, practical understanding of how modern AI actually works. Today, we start at the very beginning. Many people use the terms AI, machine learning, and ChatGPT interchangeably. But to build a real foundation, we need to see how they actually fit together. Think of AI as concentric circles, each one more specialized than the last. Today, we're peeling back those layers to see where the technology you use every day actually sits in the hierarchy. Let's dive in.
Here's the big picture. This slide shows the AI hierarchy as concentric circles. At the outermost ring, we have artificial intelligence, the broadest category. Simply put, these are machines that perform tasks that usually require human intelligence. You've been using this for years. Think of your Spotify recommendations, GPS finding the fastest route, or your bank catching a fraudulent charge. But there's a critical distinction right here on this slide: narrow versus general AI. Everything we have today, from Siri to self-driving Teslas, is narrow AI. It's brilliant at one specific task, but cannot learn to do anything else. General AI, the kind that learns any skill like a human, remains entirely theoretical and is likely decades away. Nested inside AI, we have machine learning, systems that learn patterns directly from data without being hand-coded. Then, deep learning, complex neural networks with multiple layers capable of automatic feature extraction. And finally, at the very center, large language models, or LLMs, massive text processing neural networks like GPT-4 and Claude. Each layer builds on the one before it. Let's explore each one in detail.
Now, let's zoom into the paradigm shift that made everything else possible. On the left, you see traditional programming, what the slide calls the bottleneck. In the old days, humans wrote every single rule. If condition A happens, do B. If this email contains the word free and an exclamation point, mark it as spam. But that doesn't scale. New variations emerge constantly, and every time they do, a human has to manually write another rule. It's rigid, brittle, and requires endless updates. On the right, we see machine learning, the engine. Instead of writing rules, we show the computer 10,000 examples of spam and 10,000 real emails. The algorithm learns the patterns itself. It discovers relationships that humans might miss, like subtle combinations of words and formatting that indicate spam. And it adapts automatically as new data comes in. This is the fundamental shift from programming every rule to letting the computer figure out the rules by looking at examples. And that shift is what unlocked everything from voice assistants to recommendation engines to fraud detection. It's the foundation that deep learning and LLMs are built on.
Next, we go deeper with deep learning and automatic feature extraction. Look at the visual pipeline on this slide. On the far left, we start with a raw image of a cat. In traditional machine learning, a human would have to tell the computer what features to look for, check for pointy ears, whiskers, texture. But deep learning does this automatically using neural networks with multiple layers. Layer 1 learns simple features, edges and textures. Layer 2 combines those into corners, curves, and shapes. Layer 3 assembles those shapes into recognizable parts like eyes, ears, and a nose. And by the final layers, the network recognizes the whole object. Cat, 94% confidence. We call it deep because these networks can have dozens or even hundreds of layers, each building increasingly abstract representations. That depth allows them to solve incredibly complex problems like language translation, medical imaging, and autonomous driving. Notice the timeline at the bottom. The first artificial neuron was proposed back in 1943. But it wasn't until 2012 that deep learning truly dominated, when a deep neural network crushed the ImageNet competition by a massive margin. And by 2022, LLMs went mainstream, which brings us to our next layer.
At the very center of our hierarchy, we find large language models. And this slide breaks down what makes them large. It comes down to three pillars. First, data scale. These models ingest trillions of words from the internet, books, and code. GPT-3 alone was trained on over 45 terabytes of raw text. That's roughly the equivalent of reading millions of books cover to cover. Second, model size measured in parameters. Parameters are the learnable numbers, the weights inside the neural network. Think of each parameter as a tiny dial that gets fine-tuned during training. Llama 2 has 7 billion of these dials. Claude 3 Opus has an estimated 200 billion or more. And GPT-4 is estimated at over 1 trillion parameters. The more parameters, the more nuance and complexity the model can capture. Third, computational power. Training these models requires massive GPU clusters, thousands of high-end graphics processing units running for months at a time. The cost? Hundreds of millions of dollars for a single training run. This is why only a handful of companies in the world can build frontier LLMs. It's not just about having smart engineers, it's about having the infrastructure and capital to operate at this scale.
Now, this is a really important slide, the operational matrix comparing traditional software to large language models. Understanding this difference is key to understanding both the power and the limitations of modern AI. Start with behavior. Traditional software is deterministic. Same input, same output, every single time. 2 plus 2 always equals 4. LLMs are probabilistic. The same input can produce different creative outputs each time. That's a feature, not a bug, but it does mean the results aren't perfectly repeatable. Programming. In traditional software, humans code rigid rules. With LLMs, the model learns fluid context from training data. No one explicitly programmed GPT to write poetry. It learned that pattern from millions of examples. Task flexibility. Traditional software requires new code for every new task. An LLM performs a wide variety of tasks simply by changing the prompt. Summarize this, translate that, write code for this, all from the same model. And error states. Traditional software has bugs and crashes. LLMs generate hallucinations, plausible but factually incorrect predictions. We'll dedicate an entire session to hallucination mitigation later in the program. And ambiguity. Traditional software fails or requires exact syntax. LLMs interpret context, intent, and nuance. You can ask a question in broken grammar and still get a useful answer. This matrix will be a reference point throughout the rest of the series.
Let's take a brief look ahead at concepts we'll explore in the next sessions. This slide introduces the ingestion engine, covering tokens, context windows, and embeddings. Tokens are the foundational puzzle pieces. LLMs don't read words the way we do. They read fragments of words called tokens, translated into numbers. The word unhappiness might become 3 separate tokens: un, happiness, and the suffix. Context windows represent the model's working memory limit. It dictates exactly how many tokens the model can hold in its head at one time during a single interaction. Early models had tiny windows. Today's frontier models can handle hundreds of thousands of tokens, like reading an entire book in one sitting. And embeddings are the mathematical map. Words get plotted in high-dimensional space based on their relationships. King and queen end up close together because they share semantic meaning, while carburetor ends up far away. This is how the model understands that words have relationships and meaning. We'll do a deep technical dive into all 3 of these concepts in session 1.2.
And here's a preview of the compute engine that powers everything: transformers and attention mechanisms.
This is the architecture published in 2017 that changed everything. Before transformers, models processed text one word at a time, sequentially. Transformers process entire sequences simultaneously, which is dramatically faster and more powerful. The key innovation is the attention mechanism. Look at the sentence on this slide, the bank of the river. How does the model know that bank means a muddy shoreline and not a financial institution? It's because the attention mechanism assigns mathematical weight to surrounding words to determine precise context. It pays heavy attention to the word river later in the sentence, and that context resolves the ambiguity. This is, in essence, how the model thinks. It's not following rigid rules. It's computing relationships between every word and every other word in the sequence all at once. And this mechanism is the beating heart of every modern LLM. We'll unpack the full transformer architecture in detail in session 1.3.
Before we wrap up, let's correct some common misconceptions. These are things I hear all the time, and getting them right is essential. Myth number 1. AI and LLMs are the exact same thing. The reality? LLMs are just one highly specialized subcategory of deep learning, built specifically for text. They're a small circle inside a much larger universe of AI. Myth number 2. The model learns new things from me while I use it. This one surprises a lot of people. The reality is that learning happens entirely offline during massive training phases that take months and millions of dollars. When you use ChatGPT or Claude, the model is merely running inference, applying patterns it already learned. It's not updating its knowledge from your conversation in real time. Myth number 3. The model truly understands what I am saying. This is the big one. The model does not comprehend meaning. It is an impossibly sophisticated prediction engine, calculating what token should logically appear next based on statistical patterns. It doesn't understand your question any more than a calculator understands arithmetic. The results feel remarkably human, but the underlying process is fundamentally different from human cognition. Keeping this distinction in mind will make you a much more effective user of these tools.
Let's bring it all together with the enterprise synthesis. Understanding the architecture is only valuable if it drives real business outcomes, and the data here is compelling. In financial services, customer service automation leveraging probabilistic reasoning generated $25 million in annual savings with 1,250% return on investment. In insurance, deep learning document processing reduced processing time from 4 days to just 2 hours, saving $8 million. And in SaaS, implementing LLMs for code generation increased development velocity by 35% with an 833% ROI. These aren't theoretical projections. These are real enterprise results from companies that understood the architecture well enough to deploy it strategically. And that's exactly what this program is designed to help you do. So, to recap today's episode, AI is the vision, machine learning is the method, deep learning is the multi-layered technique, and LLMs are the application we're all using today. Each layer builds on the one before it, and understanding that hierarchy gives you the foundation for everything that comes next. In the next episode, we're diving into tokens, context windows, and embeddings, the building blocks of how LLMs actually process language. I'll see you there. Thanks for watching.